right, gang, here we go. Starting Unit 2. It's more trigonometry, and if you're sick at home or whatever, just know that this section is pretty much going to take us at least two class days. So this one video, we're going to need at least 2 days of class to get through the notes. So because this one, boys and girls, is a doozy. Historically, and typically, I think a lot of people would say that this section is the trickiest section in the entire semester. But you know what? If we put enough time and energy and effort into this section, I see no reason why it can't be. I don't see why it has to be such a challenge and so difficult. So anyway, here we go. Let's start by writing down again. See, this is not even the first time we've seen this. I want to first review some fundamental identities, which we already know of from last unit, starting with the reciprocal identities or the refliprical identities, right? Remember, you should know this by heart now, like the back of your hand, that the sine of x is equal to 1 over the cosecant of x, because sine and cosecant are reciprocals of each other. So, really quick, because we're going to be using these fundamental identities a lot in this section, let's write down, again, all of the reciprocal identities and all the reciprocal pairs. Remember, cosecant is equal to 1 over the secant of x. And so pause the video if you need to have time, because I'm moving on here, to write these down. Likewise, the quotient identities, okay? We're going to be using those again. And so as a reminder, the tangent of x is equal to the sine of x over the cosine of x. And on that note, the cotangent of x is equal to the cosine of x over the sine of x. And also, don't forget about these Pythagorean identities. Starting with the most important main one, sine squared of x plus cosine squared of x is going to be equal to 1. And then we have the other Pythagorean identities that we already wrote down and looked at last unit, but we're going to be really using them. So pause the video if you need to. Let's write these down again. Now here we have some brand new fundamental identities that I don't think we've mentioned before or wrote down before, and they are called the even-odd identities. And it pretty much talks about how the sine of negative something, like the sine of a negative angle, is actually going to be equal to this. You just do negative the sine of that angle. For example, if you looked at what the sine of negative 30 degrees equaled, it would actually be like the sine of 30 degrees, but the opposite. Okay? And, so that also applies with cosecant of negative x, and it also works out that way for like the tangent of a negative angle, and of course then the cotangent of a negative angle. With cosine and secant, it's a little different. Like the cosine of negative 30 degrees would be exactly equal to the cosine of positive 30 degrees. And we probably sort of investigated this last unit, at least a little bit. If we didn't, I'm sure you could, on your own without too much trouble or confusion, kind of investigate why these identities are true the way they are, on your own. But again, these are the even-odd identities, and it's just the way they are. These are just truths that are just true. What more can I say? All right, here we go. Gonna take a sip of water. Getting into these series of examples, here's what we're actually going to be doing in this section. We're going to be taking other sort of like random, I guess, identities and verifying them. In other words, proving that they are true, proving that they actually are identities. Okay? So contrast, we have like all these fundamental identities that are fundamental. Okay? They're commonly just known to be true, you know. We're going to show that these other random identities are also true, and guess what? Part of how we're going to do that is by using the fundamental identities, which we already kind of believe are true and know are true always. And basically, here's what we're going to be doing. I mean, in practice, in action, all we have to do is somehow, some way, whether it's using the fundamental identities or some other algebraic trickery, all we really have to do is rewrite the left side and or the right side until the left side and the right side literally say the same thing. Once we can make the left side and the right side totally match, exactly match, then we're done, and we've shown that the identity is, in fact, true. Okay, so here's what I'm going to do first. I'm going to rewrite the cosecant by using a reciprocal identity. I'm going to rewrite the tangent using a quotient identity, and I'm going to rewrite the secant of x using a reciprocal identity. This is going to be a very, very common first step, or just step. Okay, it's a very common trick that we have up our sleeve. Try to rewrite everything in sines and cosines. I mean, think about it. Wouldn't that make it a lot easier to make the left side and the right side literally match if all we were using was like sine and cosine and not the other four, you know, cosecant, tangent, cotangent, etc. Okay, and over here, gang, here's what I'm going to start to kind of need you to do. This little symbol right here is basically math talk or math notation for because. So whenever you see this symbol, it's like seeing the word because. So why is this the same as this? Well, because reciprocal identity and because quotient identity, you know. And so you also have, hopefully by now, a copy of like a bunch of codes. I think that's what I'm calling them. Kind of like all of these reasons, you know, like little quick codes for saying, so you don't have to like write out reciprocal identity. Because of the reciprocal identity, because of the quotient identity, I can write this and this and this. So just kind of some shorthand. You know what, I'm going to check something real quick. I want to make sure I'm getting the right terminology. Bear with me, I'm going to check my handouts. Alright, okay, so they are, I just wanted to make sure, they are, what I am calling them are codes. So this would be the code, the quick code for reciprocal identity, and this would be the quick code. And this is, if you don't have the, like let's say you're homesick or something, you will have a piece of paper, a reference sheet, now and even on the test, that has all of these codes, so you can just kind of use the proper quick shorthand code. Anyway, moving on. Once we have it written down in just sines and cosines. Now you can look at it and see, like, how can I work more with the left side and or the right side and make them say the same thing, but by using proper algebra, by using proper use of identities. And so I hope that you can look at this and go, wait, this is just a fraction times a fraction, that when you multiply these fractions together, like, actually multiply them together, it's going to simplify. Like, this sign will cancel with this sign, and you're going to have 1 over cosine, which now literally matches. And so using the proper codes, because I multiplied these fractions together and I canceled. So there's a couple codes you need to be aware of. These ones are pretty common also. Doing some actual multiplying, and then the signs cancel. So just making sure you put down that that you know what's actually happening as you make this literally match this side. And then, since now that this matches, we're done. Okay, moving on to number 2. What do you guys want to do first? I see cosine, cotangent. Again, you're going to learn that I don't really want to work with it as a cotangent. Maybe I can rewrite that as something else. Same with this cosecant. You know what I mean? And unless you can think of something else to do, and I know I'm getting way ahead of myself, maybe I guess some foreshadowing at least. Sometimes it's going to be in your better interest, in your best interest actually, to leave it in a cotangent, because maybe you notice a way you can apply a Pythagorean identity, Like, if you see something like this, you might want to just, hey, I can just, instead of changing tangent to sine over cosine, or in this case, sine squared over cosine squared using a quotient identity, maybe I just switch all of this out with a quick secant squared. You know what I mean? Anyway, sorry. Went off on a little tangent there, no pun intended. Actually, pun intended. But in this case, I think what we're going to do is change this cotangent to cosine over sine using a quotient identity. And we're going to change cosecant into that by using a reciprocal identity. And so that way all of it's just sines and cosines. All right. Now what are we going to do? Well, these could literally multiply together, right? You could think of this as cosine over 1, I suppose. Now it's officially a fraction, but these are going to multiply together to get cosine squared over sine. That was just by multiplying, because I think that's all I did. Yep. Okay, now what do we do? How are we going to make this left side match the right side? How about we actually try to do this addition? How are we going to add this and this together? Wouldn't it be like adding fractions? And so what we need to do is, maybe, and again, I'll literally write it out. We could do that multiplying in order to give these two fractions the same denominator. And so once they have the same denominator, again, by LCD, which is like the code for I gave them a common denominator, a least common denominator, and now these two fractions can add together. So as we learn the codes here, this is the code for adding fractions together. Okay? Man, we're doing like such little baby steps at a time, but that's the way this goes, man. So all we did was add the fractions together now that they had the same denominator. And what can we do now? Man, it seems like we're getting so close. Did you notice that this right here is the Pythagorean identity? Not exactly, but it is, you know. Like, hey, this is going to be a common thing here, people. Ready? There's a lot of ways to rewrite the Pythagorean identity. You know, you could mix these up and you know, put the cosine squared first. Heck, couldn't you move this term basically over to the right side, and wouldn't it therefore be true that the sine squared of x would then be equal to 1 minus the cosine squared of x? Bottom line, if you see somewhere in your identities you're proving, if you see a 1 minus cosine squared of x, you could switch that out for a sine squared, and you could, what's the word? You could cite that as a Pythagorean identity thing. So anyway, this is just going to become a 1 because of the Pythagorean identity. So there's the code for busting out, for using as a reason, you know, why is this equal? Because of the Pythagorean identity. So hey, just like that, left side matches the right side, and we are done. All right, number 3. What can we do in number 3? Here's something sort of new. See how everything is already just sine and cosine? So it doesn't look like we're going to really apply a reciprocal identity or a quotient identity. So what else can we do to rewrite the left side and just make it that? What can we do? You know? Well, I can think of a couple different things at least. Maybe you notice that the cosine squared, see what I was just talking about? The cosine squared, if you move things around in the Pythagorean identity, you know, what would the cosine squared of x be equal to? Well, if you move this piece over to the other side, you could replace this piece, you know, with 1 minus the sine squared, you know, and then kind of go from there. But I think what I did instead was I noticed that in both of these terms, they're technically both terms, they both have a sine of x. And you can factor it out as a GCF. So if you did that, then the quick code is, well, that makes sense. GCF is your code if what you're really doing is rewriting it using factoring a GCF. So that's another algebra trick you have up your sleeve in order to rewrite pieces of these identities, is by factoring. Okay? And now what I'm going to do is bust out the Pythagorean identity, because like I've been saying, 1 minus the cosine squared, that is technically, you can use the Pythagorean identity. Okay? So, you know, it's not the way the again, I hate to be repetitive, I guess, but the traditional way we write the Pythagorean identity is sine squared plus cosine squared equals 1. But you could rearrange it so that this equals sine squared. Okay, so but the Pythagorean identity says you can replace this with that. Get used to that kind of stuff. And holy moly, just like that, do you see how you can just do the sine of x times the sine squared of x? That's the sine cubed of x by just multiplying. And just like that, we were done. So, you know, I think it was pretty much inevitable, whether you really did it at first or here. You were going to use the Pythagorean identity at some point. It was inevitable. I should say this right now, I guess. There is very, very often going to be more than one way to skin these cats. More than one way to go through steps. More than more than one strategy overall in order to show that the left side equals the right side. How about this one? Moving on. What can we do here? Looking at the left side, looking at the right side. Maybe you pause the video and give yourself a chance to think to yourself what you might do if you're already catching on to this kind of stuff. I'm noticing, like I'm thinking of a couple different ways to do it, but when I look at the right side, I mean, we've been sort of pushing that, don't really want to work with cosecant, we want to rewrite that, and we don't really want to work with cotangents. We would like to only work with sines and cosines, right? In order to make it easier to make everything match up. So, is that what I did? That is what I did. And why? What makes me okay to write this as that? Reciprocal identity. What makes it okay? Like, why am I able to write this as that? Because of the quotient identity. Learning these codes now, probably. Now what? What would you do now? Well, perhaps you look at over here and go, can I actually add this and this together? Well, they're both fractions. Hey, I could have said this earlier, but by now maybe it's sinking in that you need to know your rules of fractions. You need to remember how fractions work, adding fractions together, multiplying fractions together. Sooner or later, I think in this lesson, we're going to be dividing by a fraction. You better brush up on all those rules of fractions and working with fractions. So, hey, sorry, that's the way it goes. But these two fractions already have the same denominator, so they can just add together. Hey, we just added fractions. So there's the code for that. And hey, look at that. They literally match, so we're done. Okay? Before I move on, algebraically, we could have actually chosen to work with the left side. The way I did it here, I didn't really touch the left side at all. Just brought it down. But you could have split this up into two fractions because of how this denominator divides into both this term and this term, and you probably could have split this up into really that, and I think, what would be the code for that? I don't even know. SF, or maybe it's just like S, maybe it's just the word split. I don't know, I haven't memorized all the different codes, but there is a code for splitting a fraction into two fractions, you know what I mean? Anyway, let's go on to number 5. Look at number 5. What could we do? Remember, hopefully the first thing that you're training yourself at, even at this point, early on, that one of our big tricks is to change everything in terms of sine and cosine. So cosecant, probably want to change that. Okay, probably, unless you have a better idea in mind where it'd be more to your benefit to keep it as cosecant of x. I mean, we'll get to an example like that, trust me, but no, we're going to probably want to change. But is that all we did? I mean, over here, hopefully it's kind of, starting to, I don't know, occur to you, like you're starting to see patterns and stuff where if you have a couple fractions that are being added together, that we're going to probably try to actually add them together. But we can only add them together if the denominators match. So that's probably something in our future. Let's see what yep. Ooh, looks like I'm trying to kill multiple birds with one stone. Not that I condone killing birds all the time. So because of this step, well, yeah, RI, reciprocal identity. And because of all this, what I'm basically doing is making a least common denominator. Okay? Not to kind of make this look super messy, but what I was essentially doing was multiplying this fraction by the sine of x, top and bottom, and multiplying this fraction by 1 plus the cosecant of x. Basically I needed to multiply each denominator by the other denominator in order to make them the same denominator. Okay? Hopefully you remember enough about working with algebraic fractions where, in order to make the denominators match, I needed to multiply this denominator by the other one and this denominator by the other one. So that's what I did. And over here, and you don't even have to actually multiply these together. I'm just going to leave each LCD as this, like sine times this bubble. Don't even need to distribute. In fact, it's probably better if you don't. All right? Trust me on that. But up here, I'm going to actually multiply stuff together. Okay? So sine times sine is just sine squared. And this numerator, okay, listen carefully. This numerator times this numerator is like a grouping, this entire numerator as a quantity times this entire numerator as a quantity, which is going to basically be FOIL. I got all of this by foiling, first, well, I'm going out of bounds with the video, right? So firsts, outers, inners, lasts. Okay? To get all of that. All right? So, again, to summarize, I rewrote cosecant using a reciprocal identity to get that. And I did whatever, I multiplied by whatever I needed to in order to make a least common denominator, because, obviously the next step is going to be actually adding these fractions together now, because they now have the same denominator. Okay? So, I got this because I just now added this numerator with this numerator. And I also, did a little, I guess technically multiplying. Even if it's like a little baby multiplying, let's still write down like this became this because of just multiplying. But what else? It looks like I added fractions together. And there might also be a code. Look, there's something else. So there might also be a code for adding like terms together, because I added cosine of x and cosine of x together because they're like terms to get 2 cosine of x. Remember, it's just like adding like terms together in the past. Yep. All right. Be aware of that, people, because I was barely aware of it. I don't have the sheet in front of me right now. Okay, all right. Cut me some slack. But there is a code on your sheet, or the sheet that you will get, if not already, for LT, which means if you're adding some like terms together, cite that as a reason for, I know it's obvious, but cosine of x plus cosine of x, it's like, where did this come from? But I know it's obvious to most people, but If you put that, oh, they were like terms. Anyway, let's move on. Well, first, I guess I should ask you, what happens next? You know, I don't see us being able to work with the right side anymore, but what can we do with the left side? Well, this is going to be a common theme, people. Always have your eyes peeled for Pythagorean identity stuff. Do you see this sine squared and this cosine squared? Well, if you put them together, don't they just make a 1? So I can replace sine squared plus cosine squared with 1 because of the Pythagorean identity. And then the next thing I'm going to do is, I guess, like terms. Yep, gosh, baby steps. But so 1 plus 1 becomes 2. I know that one was really obvious, but they're like terms technically. And we're not done yet, so don't rewrite this step again. We just had this, so we already have this. Don't rewrite this again. So what do we do next, people? Man, this is a doozy. This example, right? This example number 5. You might want to star this baby or circle it because this is a really good example. This has a lot of different stuff going on with all different kinds of codes and tricks that we have up our sleeve that we're busting out for this one. So, what the heck can we do next? Seems like we've busted out every trick in the book so far, except factoring. Do you see up in the numerator, people, how both of these terms have a 2 that we could factor out because GCF? All right. And now that we did that, do you see the opportunity to cancel these two bubbles? Yes. And that is what takes us to the promised land. And now the left side and the right side literally match. Woo! That was a good one. Number 6. What can we do here? Well, let's just cut to the chase. This one might stump you at this point in time, which I don't blame you. It's okay. Don't feel bad at all, trust me. If looking at this, any tricks or strategies don't pop into your brain. I'm looking over here, and I might half expect you to go, well, maybe I can divide this cosine into both of these terms and just split it into 2 separate fractions, which would be 1 over cosine minus sine of x over cosine of x. But here's what we're actually going to do. Now, this is not something you want to do a lot, Essentially what I'm saying is moving pieces or terms or whatever, like moving things from left side to right side and sort of like interchanging things from the left side of the identity and the right side of the identity, adding things to both sides, multiplying both sides by that's something you really want to try to avoid. But in this situation, yeah, this is what I'm gonna sort of say we want to do as a strategy, okay? We are literally cross multiplying. Okay? So seeing as this has just a proportion, let's actually cross multiply. Let's multiply the cosine of x over to this side, and let's multiply the 1 plus sine of x over to this side, which is essentially what cross multiplying is. And hey, we have a code to quickly say that's what we did. We cross multiplied. CM, perfect code for that. And so we get to here, which I think we can work with this. We can just multiply these together and then just probably multiply these together. I mean, I'm just going with what I see. I see cosine times cosine, so I'm just going to do it. You know, hopefully you're getting an instinct for this. Just go, oh, I'm just going to multiply these together now. Oh, hey, this is this bubble times this bubble. I'm just actually going to multiply. Now remember, this would be FOIL. Firsts, outers, inners. Whoop, whoop. Let's start that again. Firsts, outers, inners, lasts, and get all of that. This looks a little bit easier to work with, doesn't it? Okay. So looking over here, maybe you see some like terms that can just combine, right? The negative sine of x plus sine of x is 0. They're like terms. And then, man, so like I can, do you see the end here, man? Like we're a breath away. This is all over but the shouting, as long as you are keeping your eyes peeled for Pythagorean identities. Okay? Look, people, the Pythagorean identity, that's going to be something you need to apply a lot. You know, like just accept it, okay? And whether you rewrite this as 1 minus sine squared of x, or just probably what I did is I rewrote 1 minus sine squared of x as, yep, cosine squared of x because of the Pythagorean identity. Okay? And that's it for number 6. Moving on to number 7. What I hope sticks out to you right away, besides what? Besides that, we don't usually like to keep things as secant. We like to rewrite that. So we're probably going to rewrite that sooner, if not later. And likewise, that secant needs rewritten. And so does that cosecant, because again, for like the 5th time, well, I don't know if I've said it 5th time, but excuse me. Again, we like things only written as sines and cosines. But even before all of that, I hope you see that not only is this cosecant, but it's the cosecant of negative x. That should look very weird to you, and if you recall, click, 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 click. Remember how I made it a point to show you these even odd identities like this guy? So even before anything else, let's rewrite the cosecant of negative x as minus cosecant of x by even odd identities. That's a perfect code. EOI. All right? So now what we're probably going to do is change everything to sine and cosine because of, well, it looks like it was all reciprocal identities to change everything to sine and cosine. I mean, you should know. I mean, look, I hope this isn't slowing you down and helping to your, adding to your confusion, that you still aren't quick to know that secant is the same as that. Cosecant is the same as that. Anywho, what do we do now? Well, again, I hope you look at stuff like this and go, huh, well, I mean, I can just multiply those fractions together as is. And as far as like this up here, this fraction minus this fraction, I could do that if the denominators matched, and it wouldn't be too tough to make these two denominators match. You know, I could just multiply each denominator by the other denominator, and it looks like that's what I did. I just multiplied these two fractions together to get this, and I multiplied, just so there's no doubt here, people, I multiplied, well, let's go over here so it's a little, I don't know. I multiplied by that, and I multiplied by that to make least common denominators. Oh, Mr. Falk, Mr. Falk. There needs to be one more code over here. I didn't just rewrite things because of LCD. I also multiplied. Wow. That is a potential. If someone catches me on that in class before I catch it, bonus point. Anyway, really quick. I know I'm always so darn stinking thorough. But instead of doing, instead of doing anything that we just did, what you could have done here is basically, brace yourself. Instead of doing the multiplying and the LCD stuff, what you could have done is looked at this as like a crazy complicated fraction and multiplied the entire top and the entire bottom. Okay, I'll write it out, but you certainly don't need to. I know, sorry to break up our momentum here. I probably should have just moved on, but if you were to just multiply the entire fraction by sine of x cosine of x over sine of x cosine of x, that would actually clear all of the fractions within the fractions. And now, just long story short, I'll just stop it right there. This would have been another way to go to clean all this up. But anyway, let's continue on as if we made it into this, which we did. So we already wrote this down, just kind of trying to pick up where we left off. And what do we do next? Well, considering that we just made common denominators for a reason, why do we ever make common denominators? So we can actually subtract the fractions together. Hey, subtracting fractions. Which, I know what some of you might be thinking. Isn't subtracting fractions basically like adding fractions? Yeah, but I don't know, whatever. It's probably for the best. Separate code, SF, for subtracting fractions. And now that we're here, okay, we have one fraction divided by one fraction. And I told you, I called this like 10 minutes ago, or I don't know how many minutes ago it was, but in order to divide by a fraction, we multiply by its reciprocal. So here's the code. If we ever needed to divide by a fraction, and therefore we would just multiply by its reciprocal. So we flip and multiply And now, people, we just multiply the fractions. And when we do that, this is going to cancel with this, and we are going to be done. Once again, because we multiplied these fractions together, and there was some canceling, because this sine x, cosine x canceled with this cosine x, sine of x. And we're done. Number 8. We're getting there, people. Again, you can see why this was a 2-day thing in class. Oh. And in case you're wondering what that amazing song is in the background, on repeat, it's called The Grudge by Tool. So, just in case you were curious. Anyway, number 8. What are we going to do here? Ooh! Oh man. I don't know if this is what I ended up doing here, but over here, this is one of those situations where you go, ew, I don't like tangent. We don't like tangents. So maybe I can rewrite tangent squared as sine squared of theta over cosine squared of theta, which would have been a quotient identity application, right? And that's maybe what I did. Okay, like on this written here. But this is one of those situations, people, where instead of changing tangent squared into sine squared over cosine squared, if you think of it, maybe instead you can think of the Pythagorean identities and go, well, the tangent squared is actually equivalent to, like if you moved this to the other side, the tangent squared is equivalent to secant squared minus 1. So that is maybe going to be something that you look to do instead, and that might save you some messy work. So in conclusion, just to kind of, sorry to reiterate, but to summarize, instead of using a quotient identity here, maybe you look to use the Pythagorean identity because it's tangent squared, and just trust me, that could end up saving you some work. So, but before that, and you could have replaced tangent squared right away. You know, like I said, there's more than one way to go through all of these steps in different orders or different strategies altogether. You know, like you totally could have just replaced tangent squared with, secant squared minus 1, I think it was. But what I saw first here was, spoiler, anyway, bringing out a GCF of 2, okay? And then, instead of replacing tangent squared with something, now we can just go ahead and replace 1 plus tangent squared with secant squared. Okay? But over here, you know, this fraction plus this fraction, we're going to need common denominators. Okay? So, how do we make common denominators? Well, this is another example of we need to multiply this denominator by the other one, and then we need to multiply this denominator by the other denominator. That's the only way to make them the same. And so what ends up happening is this numerator becomes 1 minus sign, this numerator becomes 1 plus sign, because whatever you're multiplying to the bottom, you got to multiply to the top. Okay, whatever we multiply to the bottom, we multiply to the top. So that's why we get this and this. And then again, you don't need to actually multiply these bubbles together for your LCD. In fact, it's better if you don't. And so, like I've said at least twice already in this video, there's a reason you make common denominators, so you can actually add the fractions together. So this numerator plus this numerator, first of all, we're adding fractions. Well, yeah. We already knew that we were applying the Pythagorean identity to turn this 1 plus tangent squared into secant squared. But, we're also adding fractions together. But at the same time, did you notice that negative sine of theta plus sine of theta are going to combine as like terms? And so we just get 2. All right? So, what do we do now? What can we do? Like the left side and the right side still don't match. We're probably going to now finally change secant squared into just sine and cosine, right? So, I'm not sure this is what I did, but because there's a couple different choices right now, isn't there? We could, well, actually, there's probably just one choice. So I'm going to assume that we're going to change secant squared into 1 over cosine squared. Yep. What makes it okay to change this into that? That's right, the reciprocal identity. Oh, but you know what else I did? I don't know, this is based on experience and just maybe instinct, but I decided that it actually was necessary, because it ends up being necessary, to actually end up multiplying these bubbles together by FOIL. Okay? By FOIL. So this becomes this eventually by FOIL, which is multiplying, and reciprocal identity. And you know what? Once again, this is potential bonus points if you want to point this out in class. Since I really just skipped all the way from like these bubbles to the final result, I pretty much skipped over, not just multiplying those bubbles together, but combining like terms together. Because check it out. The FOIL, when I include steps that I sort of just kind of brushed over, that's the steps of FOIL, the firsts, outers, inners, lasts. But the reason it's just this is because these like terms combine. So, yeah. Another chance for bonus if you think of that. Because I don't know if I'm going to be able, I don't know if I'm going to think to point that out in class or not. But anyway, bottom line, getting back to the present, getting back on track, we get here. Okay? Jeez. So I can see the ending myself. This 2 can just multiply to this fraction, but do you see a Pythagorean identity? I hope so. Always keep your eyes peeled for Pythagorean identity stuff. Always look for opportunities to apply the Pythagorean identities. And so this becomes this. So not only Pythagorean identity, but we multiplied. So cite that. Holy crap, that's it. Love this song. So, this might actually be something in class we don't kind of drag our feet through, because at this point it's actually not overkill. I don't think that's the best way to say it, but we've already beat this to death. All of these different tricks that we have to use, all the different ways to work with these identities until the left side and the right side literally match each other. But so anyway, I'll do it here in the video, and I probably am going to do it in class or did it in class. But here's the overall guidelines. Work with each side of the equation independently. Okay? The only exception to that was the one example where I said we should just cross multiply. Remember the proportion where we just kind of cross multiplied? That was the only time we moved pieces or terms or factors or whatever. We move things from left side to the right side or the right side to the left side. But other than that, you want to try to work with the sides independently of the other side. Start with the more complicated side. Yeah, that kind of went without saying, you look at whatever side you can work with, because let's be honest, people, there was examples where you really couldn't do anything with the one side, and you could only really work with the side that was more complicated, and I don't know, you just kind of do whatever you can see in a step-by-step fashion until it looks exactly like the other side. Analyze equation and look for opportunities to apply the fundamental identities. Right? Heck yeah. Including the Pythagorean. Try using one or more of the following algebraic techniques. Now usually this, in fact, always, this pretty much always involved using the fundamental identities, right? We just said that. So you're going to be looking to use the reciprocal identities or the quotient identities and the quotient identities to rewrite everything in terms of sines and cosines. Unless you see a really nice opportunity to use one of the Pythagorean identities. And it would be probably a better idea to leave, like we saw before, leave it as tangent squared for another couple steps in order to use a Pythagorean identity instead. We did some factoring. Keep that in mind, that factoring is an algebraic trick that you have up your sleeve. Separate. We never actually used this in this video. Okay? But I mentioned it. It wasn't one of the ones I ended up using at the end of the day, but separating a single term fraction into two fractions. Okay? We did this one a lot. Combining fractions together using least common denominators. Multiplying by a binomial that occurs on the other side of the equation. Is that cross multiplying? Multiply that by a binomial fact. You know what? I think this applies to something that I'm going to try to avoid mentioning about. Why is this here? This could apply to cross multiplying or mixing sides together, but I think this refers to implementing a strategy that involves a conjugate, right? Which this doesn't really explain that great if that's what it's referring to. Anyway, I'm just going to say I don't worry about number 5 right now. Whatever this is referring to, we didn't use it. And then don't be afraid to stop and start over again. Creative puzzle solvers. Know that strategies leading to dead ends often provide good problem-solving ideas. Again, like this can be frustrating. I know, like I said, this was like the toughest. Maybe, you know, like a lot of people think that this section is the toughest section in the whole semester. It can frustrate you, but hey, because it's kind of like an open-ended thing, you know. There's more than one way to attack these problems, and sometimes there's more than one way that'll work. Sometimes there's really only one way, or you can start like going in circles, you know, by rewriting something and then rewriting it back to what it was in the first place. I know, I get it. It can be a little frustrating, but learn that short list of tricks that you have at your disposal. And again, don't be afraid to stop and start over again, and all that kind of stuff. Okay? And that's that, I think.